Yes, good evening, ladies and gentlemen. And great to have you again today. Today, we will continue our earlier studies on the implementation of algorithms in terms of understanding what it is and the analysis of the algorithm. Today, our emphasis will be on the critical analysis of what an algorithm is, so as to understand the implementation of the orders. We have done a lot before now, and it is good to us also remember that when we talk of an algorithm, we were always talking about those steps in unambiguous ways to carry out some task. We have told you that an algorithm is just a small engine that runs within a program. It is not the same thing as a program, but it is just a way in ensuring that the program is implemented appropriately. We also mentioned before now that there are several ways of expressing an algorithm. It can be natural language, which is your language. We have said it can be a pseudocode. We have said it can be graphical. And of course, you know that an algorithm can be mathematical. So let us look at the example of this mathematical expression of an algorithm. And this will be our algorithm 3.0. The task here is to multiply two positive integers, a and b. So what we are saying is that there are two integers that are positive. And these integers are integers a and integers b. Now, the concern is that here we want to have an integer a that has contained a value 45. So we say 45 is an instance of integer a. 45 is an instance of integer a. Then we have another value b, value 19, that is contained in the integer b. So we also say 19 is an instance of integer b. So the task before us is to multiply the value that is an instance in a by an instance in b. Here, we know that the instance in a is 45 and the instance in b is 19. So the task here is to multiply 45 by 19 and accordingly expressed as 45 asterisk 19. Generally, the way this is done is by having an expression 45 here times 19. If you remember the way you usually do it, you say 9 times 5, it gives you 45. So you write the 5 down and take the 4. 9 times 4, it gives you 36. So you add that 4 to 36, you have 40. You write it here, so you have 4, 5. Then you come here. This is the way we were all taught in the elementary schools. 1 times 5 is 5 here, and 1 times 4 is 4. So you add this together, you have 855. So 45 times 19 will give you 845. So if you have another instance of a, say let us assume that a equals to 60, and b equals to 72. Then you have 60 times 72. And the answer you get here will be 4,320. So this approach has been the usual approach that has been conventionally used as an algorithm because it's a step-by-step procedure, unambiguous procedure, very mechanical procedure, distinct procedure to ensure that these inputs are used to generate an output. So this is input for A, this is input for B, and this is the operator that operates on A and B at this level. They are distance level, and this is the product of that. Then this is the summation of these two expressions. Remember, if you look at this summarization here, you will see that we have fulfilled all the basic elementary attributes of an algorithm. This expression is finite. You get an answer at the end of the day. This expression is complete. At the time you multiply this and this, you have a totality that gives you all the results of the operation. This expression is distinct. 45 is 45. 45 is not 46. 19 is 19. 19 is not 20. So it's distinct. So this is an example of an algorithm that is used in multiplying 45 by 19. But just like the way to the airport, from your house, there are several routes you can take to the airport. The aim and the task is to get to the airport at the appropriate time. What are we saying at this time? We are saying that there are several routes to that airport, and you will choose the one that best suits you. This explains why we can choose other algorithms to multiply the value in A times the value in B without having to go through the steps. And I quickly shared the other one. This is a different algorithm. And I want you to pay attention here. This is the multiplier. And this is the multiplicand. A is the multiplier and B is the multiplicand. So the multiplier is divided by 2, while the multiplicand is multiplied by 2. Now, the algorithm implementation here is that we pick numbers in column 2 here, when the corresponding number in here is odd. So that is the result. So we have 3 variables here: the multiplier, the multiplicand, and the results. I go here again. We have the multiplier, the multiplicand, and the results. 3 clear variables. 3 clear variables. We have the multiplier, the multiplicand, and the results. Now, if this is the multiplier, and this is the multiplicand, and this is the result, how do we use the multiplier and perform operation on the multiplicand and get the results? We say we divide the multiplier by 2, and we multiply the multiplicand by 2. So we have A divided by 2 as the multiplier, and the multiplicand is B times 2. But how do we choose our results? What is the operator here to choose our result? The operator is a logical operator. And that logical operator, we have that you pick the number in the column 2. This is column 2. When the corresponding number under the multiplier, is odd. So we have 45 times 19. Remember, we are dealing with integers. If you divide 45 by 19, what do you have? 45 by 2. You have 22.5. If you divide 45 by 2, that is A divided by 2, you have 22.5. Because we are dealing with integer, we ignore everything after the decimal point, irrespective of if it's higher than 5 or lower than 5. We ignore it because our variable can only contain an integer called 22. Now, the operator here says we multiply B by 2. So 19 is the value contained in B. When you multiply 19 by 2, you have 38. But our result says that for each of these columns, the result will be when you have an odd number corresponding under the multiplier as the number that is odd. So When you have, we now have 19 here, 45 here. So 19, so 45 is odd. Because 45 is odd, we write 19. He said, pick the number in column 2. That is, this is where we are picking the number. We are picking the number in column 2. And when the corresponding number under the multiplier is odd, because the corresponding number here under multiplier is odd. And I think this should be very clear. Now, when you divide this by 2, you have 22. We multiply this by 2, you have 38. We will not pick 38 because 22 is even, but our results say it must be odd, so this will be blank. Now, we divide further, so we assume that this is a new variable. You see that this is step 1 of the algorithm. This is step 2 of the algorithm. In step 2 of the algorithm, we say A divided by 2. So when we divide A to 2, we have 11. And here we say 38 times 2, we have 76. So because 11 is odd, we pick 76 and we write 76 here. We divide 11 by 2, we have 5. And we multiply 76 by 2, we have 152. Because 5 is odd, we pick 152 because we are picking again number in column 2 when the corresponding number under the multiplier is odd. So here, we divide 5 by 2, we have 2. We multiply 152 by 2, we have 304. 2 is an even number. It is not odd. Our rule says for us to get a result, the corresponding number must be odd under the multiplier. So you divide 2 by 2, you have 1. And you multiply 304 by 2, you have 608. But because 1 is odd, we move 308. Then we add everything. Ladies and gentlemen, you see that your answer is still the same answer as what you got when you use your conventional operator for multiplication. Your answer is the same when you use your conventional and the usual operator and operating system for the multiplication of 45 by 19. For me to understand that you get this clearly, I quickly throw this out to you, and you have to reply me by chat. If this 45 has been replaced by 25 and 19 replaced by 9, what will you have at the third stage? At step 3, what will be the values in step 3? You need to quickly respond to that for us to move on. Now we have expressed 45 as 25. Let us have 45 as 25 and 19 as 9. So what will you have at the third stage? Or what will be the product? But what I think my interest is, what do you have at the third stage? 25 here, 9 here. So what do you have? So what will be the result at this third stage? Replace 45 by 25. That is, let A contain an instance of 25 and let B contain an instance of 9. So what will you have at this step 3, at the third stage? I have seen several answers, so let's go into it. I have seen 6 and 36. I'm asking for the result. Perfect, 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 perfect. Okay, I'm waiting. I'm still waiting. I'm taking your answers. Okay, Michael, that is not correct. Michael, that's not correct. The result will not be 9. The result will not be 9. At the third stage, it will be blank. The third stage is, no, yes. So if A is 6 and B is 36, the third stage will be blank. The corresponding result will be blank because the corresponding number is odd. Because the corresponding number is even, not odd. Odd is not even, it's even. No, who got 225? No, you won't get to 25 here. We're not talking about the answer, we're talking about the thought state. Thank you very much. So ensure that you are a member of this class and ensure that you have answered this question so that that could be listed as the content of your submission we are in this class. If you do not raise up your hand at this time, you have question, please send a chat to me and I will take your question. So you may wish to stay down your hands, that will continue with the class. So that's been said. So what we have as 45 and 19 are called instances of the containment of variable A and B. An instance of a problem is just the value, a specific assignment of values to the parameters. So where you have a problem, an instance of it, for example, you have students in this class, an instance, each of you is an instance of the student in this class. That is what we call an instance. This problem can be used for multiplying two positive integers. So what we say is that when you have 45 and 19 as an instance of that problem, you can even when you have 25 and 9, or you have 42 and 6, or you have 80 and 2, they are also instances of the variables A and B. So most problems have infinite collection of instances. That is, when you want to literally, you could say this is an example of the type of problems. So you have unlimited, infinite collection of instances. So therefore, when we say you have an instance of a problem, it means that if you have a particular value, other values that satisfy the conditions of the earlier value can be termed as an instance of that problem. So therefore, we can define the domain of that problem as all the set of instances that can be considered that are suitable for that set of problem. So now the above algorithm will not work if the first operand is negative, because we said that we are talking about positive integer. This does not invalidate the algorithm, because it's minus 45 and 19 is not an instance of the problem to be considered. Because if you look at the problem that we mentioned earlier, we mentioned about positive integers, where we say they are positive. Going further, we look at the order. Now, when you want to compare algorithms, we usually use what we call the frequency count. We usually use the frequency count. What do we call the frequency count? Consider the three programs that is stated before you. Consider the three programs stated before you. I think that's clear. We have that x plus y, and the value is returned into what? X. X plus y, the value is returned into x. Now, we also, that is for A. We also have a B that says that, oh, let us do the same operation for the x of y from 1 to n for each value of I. So let us consider I for the same operation x plus y that will put the product into x for 1 to n. So if we are looking at I from 1 to n, let us do x plus y and put the value into x again, and we repeat that operation for 2, 3, 4, 5 till we have to the n, and we end it at n. But C says that let us even consider two of these variables. One is I and the other one is j. So let us consider the same operation for x plus y, having the value back to x, when I goes from 1 to n, and j also exists from 1 to n. So for each value of I can exist as 1, another instance of I can be at 2, and it can go on and on and on to n, and also j from 1 to n. Now, the frequency of the count of this statement, this STMT is the short form of a statement. The statement x is plus y is, put the value into x, is 1, n and n squared. That is the frequency, because we are saying we want to look at the frequency. The frequency here is 1. The frequency here is n, because we have only 1 to n. Here it is n squared, because we have the operations for 1 to n at one instance, and another 1 to n at second instance, so it's n squared. So irrespective of the machine you use to run this program, irrespective of the machine you are using to run it, we know that the execution of B is n times the execution of A. This is very important, ladies and gentlemen. Irrespective of the machine, if you use a processor a processor with 50 cores, a processor with 100 threads, a processor with 2,000 threads, a processor with, no matter how fast or how smart your system is, the processor is, no matter how smart it is, no matter how large the board setting is, we know that B is n times A, and C is n squared of what? Of the operations in A. So this is about the execution time. If this is executed in 1 second, then we say this is executed in n seconds. Then this will be executed in n squared seconds. So it's about the execution time. And that's why we say that the order is simply understood by the time we look at the frequency counts. The order is frequently understood by the fact that the order is frequently understood because we have frequency counts. I have logged the class. I have logged the class to that limit because I wanted people to be in at the appropriate time. This is a very important class. Those that cannot join here should join the channel on YouTube. The link is available and they can join the channel on YouTube. So pass the message across. Now, so you usually have the frequency count to compare the algorithms. And then we consider the following. One, we consider the operator when the operation is singular definition. We also consider the operation when you have more than one instance of that operation. And we'll consider the operation when you have repeated operators requiring several operations. Ladies and gentlemen, it means clearly that the frequency count can help us to manage and understand the order that is used in comparing algorithms. What is very clear in this page is that what is very clear here is that we have 3 different algorithms. 3 different algorithms. And our interest is in comparing these algorithms. Our interest is in comparing these algorithms. So if it is in comparing these algorithms, how do we compare them is the question. And that's why we're on this page. We compare them by using what we call frequency count. The topics we are learning today is very, very essential. Is very, very essential. And now, because we are saying we are looking at the order, let us go and look at the existing orders. the descending order. The first one is what we said earlier that we call the big O notation. That's the first one. We call it the big O notation. Now, f of n equals big O, because that's what we are saying. This is the big O. This is the big O. F of n equals the big O of g of n if and only if there exists two positive constants c and c naught, such that f of n is less than or equal to the constant by g of n for all n greater than or equals to n naught. So what we are saying here is that f of n is less than or equals to the product of this. That is when you multiply this constant by g of n, it is still the g of n. It is still less than or equal, it is still greater than or equal to f of n, because this is saying that f of n is less than or equal to cg of n, which means that cg of n is by the time you add this product, you know they are equal here. If you look at this one, f of n equals to big OG of n. But by the time you find the absolute value of f of n, we are saying that the absolute value of f of n will mean that you are introducing a constant c and n naught, such that the cg of n is greater than or equal to f of n, because f of n is less than or equal to cg of n. But this will only be true for all n greater than or equal to n naught. So you will not have an n naught that is greater than or equal to n. N naught will be less than or equal to n. So what this means actually is that if you look at it now, that this g of n is greater than or equal to f of n, means that g of n is the upper bound of the function f of n. Look at this operator here. Cg of n is greater than or equal to f of n. And that's why we said f of n is less than or equal to cg of n. So because cg of n is greater than or equal to the f of n, it means that g of n itself, the g of n here, is the upper bound of f of n. Is the upper bound of f of n. So when you look at this here, you say, look at this graph. So this is n naught. We are saying that this means that if this is c g of f of n, this is f of n. So this one, this operator here, cg of n is the upper bound of this function. So no matter how f of n grows, it will not grow higher than cg of n. That should make some sense. Very, very interesting calculation and quite simple to understand. No matter how f of n grows, it will not grow higher than cg of n, because we said that f of n is less than or equal to cg of n, provided that there's this n naught that is just greater than this n greater than or equals to n naught. So this is what we have. So this n is greater than n naught. So it's a value from here. And that's why you are picking that value from here. You see that it grows and go to the cg of n. So this is the illustration for the big O. Excellent illustration there. So let us have examples. So we want to test. We want to test that is 17n squared minus 5n equals to big O n squared. What we have to do is simple. We know the representation of this. We know that this is the same thing as saying that see here, this thing, this expression, we say that this one, the big O of n squared is like we are saying that we are saying big O of g of n. If you look at what we have here, the big O is g of n. So if you come here, so this, all of this is f of n. What we have here, 17n squared minus 5n, just put it in place of f of n. So f of n, so at the end of the day, you are reckoning with this expression, f of n equals to big O g of n. So if you come here and you say f of n is this, so f of n is 17n squared minus 5 equals to big O of g of n. So g of n is n squared. Now, it means that, and we say that f of n, if you to the next stage here, the f of n is less than or equal to, now we are not using the equality sign. We are expressing it as f of n is less than or equal to cg of n. Now, so it means that f of n equals to 17n squared. So this is cg of n. This is g of n. So we have c equals to 17 and n naught equals to 1, because all of this will exist when n is greater than or equals to n equals to 1. Now, so if this is the expression, that therefore we can have 17n squared minus 5n equals to big O n squared. 17n squared minus 5n equals to big O n squared, because we have been able to represent this as a representation of f of n equals to big O of p of n. The same thing can be applied to this expression, because what question you should ask is that, why did we put 17 here? We know that this is 17n squared minus 5. And 17n squared minus 5 equals to this. This is the function. N squared is the highest function here. Is this highest value variable there. So it means that everything here, for it to be the nearest thing, it can be less than, that we can guess, because we don't know what n is. The nearest thing it can be less than is when we have 17. So if let us say n is 1, if this is 1, so 17 minus 5 will be less than 17 times 1, which is 17. So because we know that this value has reduced 5. Whatever value you get, you have reduced 5. So because you have reduced 5 here, so I'm teaching you this trick. This is what they call the trick in understanding the big O expression, or the order, or calculating the order of growth of a function. It's called the trick. This is the value here of fn, and we know that fn equals to this. But now we are saying that this expression, if you come to our earlier equation, if our earlier definition, that this expression is less than here than c, because we are introduced a constant for the g of n, and that will exist if n is greater than or equals to n naught. Now, for this value to be less than g of n, cg of n, you need to get a c that will be the supremum, the lowest higher bound of this. That will be the lowest higher bound of this expression, of this function. So let us assume that the least thing that can happen here is that our n is 1. So because we have this value, we will be safe to say that this, because 17n here, 17n squared, 17n squared here, this expression of f of n, when you remove 5, it will definitely be less than 17n squared. So we are comfortable to say, let us put our expression as this. Of course, constants can be anything. Because it is good for 17, it can be good for 18 and 19. It will also work for 18 and 19. And that's why we are not concerned about the actual value. Rather, we are working about the admissible value, what we call the admissible value. So we have 17n squared here, and for n less than or equals to this. So you have this expression, and you justify that it is correct, that this expression is correct. So that's what we have justified here. 17n squared minus 5n equals to big O n squared, which is correct. So you can use the same techniques and trick to calculate every other expressions in big O. I will be sending you assignments on that, but not for tonight. So now we have complexity classes. Complexity classes, which is determined by the growth rates. By the growth rates of those classes. We have from the n factorial to the polynomial to the linear time, but we are going to express that in a more admissible way by looking at the way the machine executes 1 million required operations per second. And we are comparing algorithm, because you should know that all of these are just ways to compare an algorithm. So now that we have an algorithm that is going to operate on one that is going to perform 1 million operations per second, we want to see how algorithms 1 to 5 performs. over the simple set of algorithms. But today, we will not be going into comparison of this. We will rather be re-emphasizing what we have done earlier. And on that note, I will want you to quickly look at what I have highlighted. Is 35n cubed plus 100 equals to big O of n cubed? You have to answer that and discuss. So you're not only going to give me an expression. This is the solution here, but you will need to discuss. So perform this for n raised to power 2, for n raised to power 3 rather. Perform this for n raised to power 3. Perform the same operation for n raised to power 5. Then perform the same operation for e raised to power n. When you have n raised to power 3 here, so do n raised to power 3, n raised to power 5, then e raised to power n. And you write the answer in a sheet of paper to be submitted with all your credentials written on it and submitted to me accordingly. On that note, we are going to end this session. And we are going to end this session by considering what we have done earlier, which includes the earlier part of the class, and that will give us opportunity to ask questions and make comments.